All right, friends and neighbors, welcome back to another CCNA networking video. We are working through Chapter 25, Fundamentals of IP version 6, or just IPv6. This video begins the start of Part 7, and Part 7 is really just all about IPv6. So there are like 5 chapters on IPv6, I think that's right. So we'll talk about some of the key topics for this particular chapter, Chapter 25. And the exam section that we're going through is Network Fundamentals, Configure and Verify IPv6 Addressing and the Prefix, and describe some IPv6 address types. Now in this one, we're not going to talk too much about the IPv6 address types. We will be going over structure and then how to expand and contract them. And then of course we'll do the "Did I know this already?" questions. So our key topics will be the similarities between IPv4 and IPv6. It turns out that a lot of people freak out when it comes to IPv6, and that's mostly because they're looking at these crazy addresses. But once you get used to those, you find out that IPv6 and IPv4 have a lot of similarities, and so we'll cover some of those. And in this video, we're also going to talk about the rules for abbreviating IPv6 addresses. IPv6 addresses are 128 bits in size. They're enormous, compared to IPv4 addresses, which are 32 bits in size. So just getting used to those is hard enough, but we've got a tool at our disposal, which is to make that giant sort of address shrink to make it more manageable. And so we've got to know how to recognize those, we got to know how to expand those, how to abbreviate them. We're also going to talk about how to recognize the IPv6 prefix. It turns out that we can do a CIDR type notation. And so we just get used to looking at that address, and then we say, what's the prefix length? And there's our subnet address. So off we go. So getting introduced to IPv6, it was supposed to be a replacement for IPv4. Now IPv4 has been around since, well, a long time. Most of the RFCs that we talk about in networking today date from the 1980s, and the ideas were from before then. That's just when they wrote them all down. But the problem with a 32-bit address space is that it's not an enormous address space. At the time, it certainly seemed enormous. We can put millions of addresses in there, but it's not big enough for all the things that we do today. Now, we also know that our use of the IPv4 address space was inefficient. The whole class full structure is very inefficient. So class A, B, and C, very inefficient. So CIDR notation was a way to make that more efficient and to make us use variable length subnet masks to just get the address space that we needed. And that helped. But really the problem comes down to eventually we were going to run out of address space. Now, in order to make this work, that is the change from IPv4 to IPv6, well, you got to teach the nodes a whole different way of doing things, at least in terms of the addresses. So the routers had to understand the addressing, the routers had to understand networks. The hosts had to be able to figure out the addressing as well, but also how to find nodes on their own network. So today, the RFC that we refer to most in this is RFC 8200. Now, the early version of this is RFC 2460, and that both of these documents have the specifications in them. Now, just a little bit of history. In the 1990s, the internet became increasingly popular. Right? We had the network access point structure that allowed more and more folks to connect. We had the first browser coming around. And I don't know if you remember the commercials for the iMac, right? Jeff Goldblum was dancing around talking about the party that was the internet. So more and more folks wanted to join, right, the party. But we also have increasing numbers of devices that aren't tied to a human directly. So I've got this machine that I'm working on. There's another desktop over there. My phone has an IP address, and any IoT devices that we have. So security cameras and sensors and refrigerators and PlayStations and all of that stuff needs an IP address. So lots and lots of devices that require additional address space, right? So they're all using up these addresses in the address space. So in 2015, ARIN, the North American Regional Internet Registry, announced that it was officially out of address space. There were some emergency addresses left over, but there were no more classes of address to be given out, and no more big chunks of address space to be given out. So they have an article out there that talks about the IPv4 address exhaustion problem, and this is referenced in the chapter as well. And there's the link for it, but you can just go out to aaron.net and read about how they ran out of addresses. And this is not just the North American RIR, all of them were having the same problem. Now there are several solutions, and we break them up into two classes, short-term solutions and long-term solutions. Well, I already mentioned CIDR, right? The more efficient use of the address space that we had based on the classes. So this was just more efficient use of the IPv4 address space. So instead of getting a full class C, which is 256 possible addresses, you could get a subset of that, right? You could get a chunk of address space that was sized for your network. Now, another short-term solution was the network address translator. And this was a box that converted an IP address to another IP address. Now, if you combine that with the use of private address space in RFC 1918, you have a solution that says I can have a whole bunch of private addresses, and then they appear as only one globally unique address. So when I talk about the exhaustion of the global IPv4 address space, we're talking about publicly available IPv4 address space. So private addresses, you can use as many of those as you want. And we know now there's the 10net, the 172net, and the 192.168net. Those three are private addresses. And so the idea is that you could have hundreds of machines that all have a private address, and they all share only one public IPv4 address. It's way cool. And in fact, there are lots of folks that say the success of network address translation is one of the reasons why we haven't had more widespread IPv6 adoption. Now, the long-term solution for the address exhaustion problem is IPv6. Now, there was a fun fact here. Why are we doing IPv6 instead of IPv5? Well, there was an IPv5 that never reached the standards process, so that's why we're at IPv6 now. And there are websites that globally track the use of and the adoption of IPv6. In fact, there used to be an IPv6 day where folks were supposed to take the switch and move over from IPv4 to IPv6. All right, IPv6 routing. Well, essentially the routing works exactly the same way that IPv4 routing has, right? We still have routing tables. They're just based on IPv6 instead. So in the screenshot above me here, that's an IPv6 host table. And you just have to get used to looking at those weird addresses. And then you realize that, well, if I'm trying to get to destinations, I'm trying to get to nodes with a particular IP address or a network with a particular subnet address, well, I still have to do the same thing. So we still have to build and forward packets. We're building IPv6 packets instead of IPv4 packets. So you have to get used to the header. Header's a little bit different too. We still need a default router or gateway. So when you get off of your IPv6 network to go someplace else, you need a router to do that. We still do the de-encapsulation and re-encapsulation across routers, right? So we destroy the Ethernet frame. So Ethernet's still the same thing. TCP still the same. UDP still the same. But we go across the router, we get rid of the Ethernet frame, and we build another one. Same thing that we did in IPv4. We also have to learn how to process an IPv6 routing table. And you can see there's some things that look familiar, right? There's what looks to be CIDR notation, right? It's not exactly CIDR notation because we're not the classless thing anymore, but at least in IPv4, but that looks the same, and so it behaves the same way. So both the host and the routers need to figure this out, the routing formation of packets. So we still have, you can see by the notation, we still have this idea of a prefix and a suffix, and we've got a mask associated with the IPv6 addresses. We think probably more in terms of binary ones and zeros than we did 255s and zeros, right? The base 10 numbers. But that's about one of the big change. Lots of IPv6 protocols. So the RFC 8200 has the specification for IPv6, right? What does the header look like? What are the addresses that we're worried about? Those kinds of things. But that doesn't mean that that automatically fixes things like OSPF. So those protocols had to be rewritten to support IPv6 routing. So EIGRP, RIP, OSPF, all of them had to have an IPv6 version. In addition, ICMP, we don't think of it as ICMP v4, but it is. So RFC 4443 gives us ICMP version 6. So the messages, it's still error messages and informational messages, but we have new messages for IPv6, and we have this thing called neighbor discovery, which uses a lot of ICMP messages. And so those are a big part of an IPv6 deployment. So there are lots and lots of RFCs that talk about IPv6 or relate to IPv6 in some way. But let's start with the addressing that we find in RFC 8200. So these are the kinds of things that you have to do for the exam. You have to be able to write and interpret a 32-digit abbreviated and unabbreviated IPv6 address. So IPv6 is 128 bits. You might be able to rewrite an IPv6 128-bit address in 32 digits or 32 bits. You might be able to get away with even less than that. So we have to understand how to unabbreviate and to abbreviate these large IPv6 addresses. We need to be able to work with the prefix length, right? That's slash. The most common one that you see is a /64, which is half of the IPv6 address space. And then we need to be able to figure out the prefix from an address and a mask. So here is an example of an IPv6 address. Now, if you see here, it's a 2340:1111:AAAA and so on. So there's a couple of things that we want to understand about this particular address. Any IPv6 address that you're going to look at, you can look at these chunks, right? So there are 8 chunks in an IPv6 address space. Each chunk is 16 bits. Now each chunk or chunk is a quartet. And it's called a quartet because there are 4 hex characters there. So 4 hex characters, each 4 bits, gives us 16 bits for each chunk of address space in an IPv6 address. So if you do the math, right, 8 times 16, you get 128. So we have to remember our binary to hexadecimal conversions for all of these, right? If you were going to convert this to all binary, your ability to do that would really, really help. So that's all this manipulation and your ability to understand what you're looking at here is what you're going to need for the exam. Now, when you take an IPv6 address, it's very common to abbreviate it or make it smaller. And then if you're given an abbreviated address, we want to be able to expand it to see the full thing. Now, there are 2 rules that we have to pay attention to. Inside each quartet, you are allowed to remove any leading 0. So if you look at a single quartet, remember there are 8 of them, if you have something like 0001, you can convert that to a 1. If you have 4 zeros, you can convert that to a 0. So that's one rule. You can suppress leading zeros in any quartet. The other thing that we can do is if you have multiple quartets that are all zeros, you can replace the longest collection of those with a double colon. You have the colon that goes along with that quartet space, and then you can replace all of those zeros with another colon. So the example from the book is right here. We see, right, this. Now I'm going to point out 2 things here. We have this 2 sets of zeros, right? 2 quartets of zeros, but there's also a 3 quartet set of zeros. You're only allowed to do this once. So you take the longest one and you replace the whole thing with a colon. But you can't do that with the other one, right? So we can do that with this one. We can replace this whole thing with a colon. But this one here, we're just going to suppress the leading zeros. So we still have 2100. We can't suppress the following zeros, but this second quartet becomes just 0. This quartet becomes just 0. 0001 becomes just 1. And then we can replace all of these with a colon, and then we suppress the leading zeros again. So if you see a double colon just like that, you know that's where a whole bunch of zeros were replaced. Now, you can only do this once, because if you did this more than one time, you wouldn't know if the number of zeros that was replaced was 8 or 16 or 24, right, you would have no idea. So you can only do it once, and you fill up the space until you can't put any more zeros in there. Now, when you expand addresses, you would do the exact opposite. So right here, what I would do is I see the double colon, and I would just expand. I would just fill that out with all zeros. And then here where I see 56, I know that I've replaced the leading zeros with nothing. And so I would just put 2 zeros right there. And I would put 3 zeros in front of the 1 and so on. Prefixes in IPv6 are just like those in IPv4. You have this idea of a network portion and the host portion. The prefix length specifies how many bits to the left, right? Hopefully that's the right direction in yours, but the network portion is shared by all nodes in an address space. So if you think about an IPv4 address space like 192.168.1.0/24, all of the addresses share a 192.168.1 in the prefix. Same thing in IPv6. The difference is that your prefix lengths can be much, much longer. So the values that you can put in there for a prefix length are 0 to 128. Like I said, the most common one you'll see is a /64, but you could have something much larger. If I had a /128, just like a /32 in IPv4, I would be talking about a particular IPv6 address space, or particular IPv6 address. There's no dotted quad notation here. We're just dealing with these quartets of 16 bits. And so if I was going to do an example here, I would take a look at this address right here. And we know now that this is an address that has been shrunk, right? It has been shortened up. And what's been done here is that we suppressed all the leading zeros. So all the leading zeros here. Now, you might ask why it's not a double colon there. And the answer is that you have to have 2 or more quartets to do this. So I would just make this 4 zeros. This would be 0001, 000A, and so on. And what I would find out is the /64 says, well, take the first 64 bits of that address space. Now, the shortened version of that would be 1, 2, 3, 4 quartets. Why? Because 4 times 16 is 64. So I would just take the first beginning part of that, and that would be the prefix. Now, to be perfect, I ran out of room here, but you would also add all zeros to the rest of that. So you would have 64 bits of all zeros. We'll do a couple of examples here in a bit. Now the /64 as a network size, how many hosts do you have on that? Well, you have 64 bits of address space for hosts. So the address space is enormous. So there's a formula or a rule of thumb here. Copy the P bits where P is the /P. So in this case, the P is 64. Change the rest of the bits to zeros. So I would copy the first 64 bits here, right? Change the rest of the bits to 0, and that would be the prefix. So that's how you figure out what it is. Now, multiples of 4 are easier to deal with. So 60, 64, 68, 72, 76, because each 4 bits is a hex character. So that makes your life a little easier, but there's nothing at all that says I can't use any number I want to. So here are some additional examples from the chapter. This is table 25.4. And I'm just going to do 2 examples here. I encourage you to try them. The answers are in the book. But if I want to abbreviate this IPv6 address, well, what I'm looking for is those really, really long series of zeros, right? If I have at least 2 quartets, I can get away with an awful lot. But I don't have that in this particular case. So my second quartet would just be 0. In my third quartet, I can suppress these leading zeros. And so I would get 1, 0. Here, I can suppress 1 leading 0, so I'd be 1, 0, 0. There's no leading zeros to suppress here, nothing to suppress here, leading 0, and then nothing. So the answer to the abbreviation would be what's on the, it's right above me here. So 2340:0:10:10:10:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:100:1 colon ABCD colon 101 colon 1010. Okay, so the next one does have some stuff we can do. Now, there's a trick here, or a trap. There's 3 zeros of quartets, or 3 quartets that are all zeros, and there's 2 here plus a little extra. Now, the rule is that you can only use that double colon once, or replace everything with a colon once. So you take the longest one. So that would be right here. So that's why over here it's 210F colon colon, and I can get rid of all of this. So the first 64 bits is abbreviated to 210F colon colon. Well, I'm left with most of the rest of this, but I can suppress the leading zeros here, and here, and here. So it just comes out to be 00D. Now, if I want to expand, I do those rules in reverse. We're just working backwards, right? So if I see something like this, I know that this is 0 suppressed. I just expand it to the 4 zeros. 0 suppressed, no suppression here. So I just add the zeros where necessary. I've got a 0 suppression right there. So that's why the answer works out to be what it is. But what we're trying to do here is figure out the prefix. So if I take that whole thing and I realize that what I was after was a /64 prefix, expanding the whole thing out shows me where the prefix is. Then I could, if you're really good at this, right, you don't have to do the expansion to figure out what the prefix is. But if you want to do it in 2 steps, you do the expansion, figure out the bits, and then do the abbreviation again. So counting these, I know that I've got 4 quartets, or 64 bits, and then I could abbreviate these again. Or if I said, oh, well, that's 64 and I need 4 sets of values separated by a colon, I would just go 1, 2, 3, 4, and that would be my value. All right, here's a little more challenging one, only because it does have the double colon in there. Well, if we look here, I've got 4 quartets, and we know that each quartet is 16 bits, so I could work this way and say I'll go to 64, and then the rest must be the prefix. I could expand, like I've done here, and I just said, well, I've got 1 quartet here and 4 here, so I'm going to fill in 3 quartets of all zeros, and that would be my 64, and that would be the resulting prefix. And then you shorten the prefix again, and you would get exactly what you're seeing here. Now, the reason it's colon colon is because we put all zeros here, right? So we see the colon colon 64 here, but it looks much shorter down here, but only because we started with zeros. Then we're going to replace all of this with zeros to get the prefix. So there you have it. Hopefully you followed those examples. Do the examples in the book. Make sure you understand how this works. But right now, let's do the chapter questions. Okay, did you know this already? Which of the following was a short-term solution to the IPv4 address exhaustion problem? Well, we know the answer there. CIDR was one of them, but in this particular question, the answer was C, network address translation. Question number 2, a router receives an Ethernet frame that holds an IPv6 packet. The router then decides to route the packet out the Ethernet WAN link. Which statement is true about how a router forwards IPv6 packet? Well, we know that any router that gets an IPv4 packet destroys the Ethernet frame and then builds another one on the other side. The same thing happens here. So the answer was A. Question number 3, which of the following is the shortest valid abbreviation for FE80? By the way, that's a link local address. And then look at all these zeros. Look at all the quartets with zeros right here. But we got another one. Which can we suppress? Well, the longest one. We can only do it once, but we can do leading zero suppression. So that's where we get the answer D. Question number 4, which of the following is the shortest valid abbreviation for the following IPv6 address? Well, it's a little weird. We've got stuff in almost every quartet, but we've got a whole bunch of zeros that we can suppress. So that's why we get the answer B here. Here we couldn't use the double colon, right? Even though we got lots of zeros. And we can't do the following zero suppression, only the leading zero suppression. Which of the following is an unabbreviated version of an IPv6 address? So you got to take this address and figure out how to expand it now. We see the double colon. So if we filled in all of these with the leading zeros that we know had been suppressed, so there's a 0 here, and then 2 zeros there, and then we just fill in the rest, with all zeros where the double colon is, that's our answer. Choice A. Question number 6, which of the following is the correct abbreviated subnet prefix for an address 2000 so on, this IPv6 address? Now this one's already expanded for you, and so all you have to do in this case, because it's a /64, it's an easy one. Where is the 64 bits that we need? Well, the prefix would be 2000 00 and then 5. And then if we want to abbreviate this, we can do the zero suppression here. Now, why can't we do a double colon here? Well, the answer is that we're going to convert all of these to zeros, and that would be 4 quartets, and we can only do it once. So the correct abbreviation of the prefix is choice C. All right, chapter 26, we're going to continue with IPv6 stuff. Now, each one of the chapters, these are getting kind of small, these chapters, because each one of them tackles an aspect of IPv6. And so in chapter 26, we're going to look at the global unicast in particular, and then some of the regional internet registry allocations and the IANA, the Internet Assigned Number Authority assignments that we see there. So we're going to be looking at a particular kind of address and how we would communicate with the rest of the world. All right, so this has been getting started with IPv6. So this video was a little late coming out. We're in the middle of finals week here at the Rochester Institute of Technology. A lot of grading, a lot of finals, a lot of lab work. So apologies for being a little late on this one, and that might be the case for the next couple of weeks. We'll see how this goes. But really what we're doing at this point is getting used to some weird numbers. We learned how to do abbreviation and expansion. But we also realized that IPv4 and IPv6 share some similarities in terms of how they handle routing and the prefixes. We just have to get used to quartets instead of dotted quad and 128 bits instead of 32. Well, all right. Like and subscribe if you're hard charging with IPv6. No matter what kind of new addresses you're using, may those packets always reach their destinations. It's routing, it's IPv6, but it's still routing. And remember, this is CCNA. You can do this.